So I think this is going to be one of the best episodes of First Principles ever. I mean, there are so many concepts that we can talk through. We're going to talk through everything from how electrical circuits work to how you generate massive pulses of power to what you can use those massive pulses of power for. Just to kick us off, why don't you tell us who you are, what you're building, and why it's important?
Yes, thanks for having me here. So I'm Btaiche. I'm the founder and CEO of Fuse, and Fuse is on a mission to accelerate the world's transition to fusion energy. And so what we're doing is creating a very high electromagnetic pulse without magnet and without laser to implode a can that has the fusion fuel that will give us, clean, limitless energy to power the future.
That's awesome. It's basically a huge shock generator. It's a big pulse of power that is concentrated both in time and in space. Is that right? You want it to be super precise, like it hits exactly the spot. All of the combined capacitors basically hit in the same spot at the same time. Is that like a simple way to put what you're doing?
Yeah, exactly right. So think of like we're creating a massive lightning in a bottle and we're using all that power to implode a can of fuel. Think like a Coca-Cola can that has, the deuterium, tritium, or whatever fusion fuel you want to implode, and use that lightning bolt to essentially crush that can and create the conditions necessary to create fusion.
That's so cool. That's so awesome. I think the coolest part to me is that at some point, so at like whatever, it's like hundreds of nanoseconds or something,
Yeah,
like a very short period of time. But for that period of time, you're generating more electricity than the whole world, than like the whole US at least. Like it's a huge amount of electricity.
Yeah, essentially. So the Z machine at Sandia, which exists today and it's been up and running since early 2000, is an 80 terawatt machine, and that's the whole world's power production is like rough 5 terawatt. Now the difference again is that it's for just a few nanoseconds, but just it gives you an idea of how much power is created to create that implosion. And also, to be fair, while the conditions created on the Z machine are very extreme. So the Z machine will create temperature in that plasma and that fusion fuel hotter than the sun. So it's really extreme conditions of temperature and density for a very short period of time that will create the conditions necessary for two, hydrogen isotopes to fuse together.
Yeah, I mean that's one of the craziest things. And for people who aren't familiar with fusion or like don't know about the other technologies that are used to make it, I think that it's helpful at a really high level to know that it's what's happening in stars. It's what's happening in our sun right now. It's very hot in there. It is very, very, very high pressure in there. And so while we could never, ever get something that's that high pressure on Earth, like there's just too much mass in the sun. Even if all the Earth's mass was used to create that pressure, we couldn't do it. So instead, we trade that for temperature. Yep. And we've created temperatures on Earth that are hotter than anything else in the solar system that we know of, like hotter than even like exploding stars. Then that's what's in your machine that you're building. It's crazy.
Yeah, so it's actually, you're exactly right in the sense where we don't have the gravity and the weight or the mass of those large planets. So how do we create this triple product is what the fusion community calls of density times temperature times confinement time. So how long can you hold these conditions together? And in some approaches, there's the tokamaks that try to have less extreme conditions, but for longer time. But in our approach, which is magneto-inertial confinement fusion, which is combining, it's halfway between the tokamak and the high laser, the large breakthrough. And in those conditions, we're going for higher temperature, higher density, but for, shorter period of time.
Totally. Okay. Well, with that as the context, let's jump into like how it actually works. I want people to leave this episode like feeling like they at least kind of conceptually understand how you would, build something up from the ground here. And to your credit, you've actually done a lot of like publishing on this exact thing. This is not some like deep secret. Like you've done peer-reviewed now papers, or are they like through peer review, or they're like going through peer review? But you publish papers like to this effect.
Yeah, they're going through peer review, but they're on the internet, so people can find and read them now. They're pre-printed, and we have other peer-reviewed paper that we've published as well that have been peer-reviewed and published.
Yeah, it's awesome. We're not breaking any state secrets on this podcast, but it will be cool to like help people understand really the fundamentals of like what's going into it. What is the electrical design that can spin up to be at the point that at the end of it, we have this crazy lightning strike star in a bottle.
Yes, absolutely. So the building block of what we've done. So to be clear, I just want to say that these conditions have been created for the past 60, 70 years. It's like pulse power is very core to a lot of systems, telecommunication, radars, etc. all function on pulse power. So what Fuse and the team has done on building Titan, which is what we call our own pulse power driver, is just to create a new system that's double the efficiency, a third of the size, that has much higher frequency or repeatability at those high energy and high power conditions. And so the way that it works is it starts with two components. It's a capacitor and a switch, right? And a capacitor, you can think about it as a battery. So it stores energy and then it discharges in a form of electrical current. And it's really simple, just made of aluminum foil with some dielectric between them, like plastic or ceramic or something. And then you wrap them, and that's essentially what a capacitor is. And a switch, just switching electrical current. So it's really that simple and basic. And so we just put a lot of those capacitors and switches in a unique configuration that allows us to store the electrical energy and then discharge it in a fast way. And power is energy over time, right? So the faster you discharge it, the same amount of energy can give you more power. Now, to be clear, there's lasers that are, we'll say, petawatt class, but they're at joule level energy, but picosecond rise time. So what we've done is still at the 200 kilojoules. So it's very high energy, which makes the problem much harder. But this is essentially the building block of how do we create the energy, store it, and then electrically discharge it in a fast way to get high power.
Yeah, I mean, just at a super, super high level, like the perfect system is one that has a high, whatever charging power, like you're putting enough energy into each of those capacitors. It can release that energy as fast as possible. Just like, what did you just call it? Like the discharge time or something, just the amount of time it takes to get rid of that energy out of the capacitor and into the rest of the system.
Yeah.
You want it to be perfectly timed. So all of these capacitors, like what you're saying is we have these capacitors, they are, it's two of them, right? And then they're connected by the little switch.
Yeah.
And then those two, there's a stack of however many of them in a ring, basically, around the thing. So you want all of those capacitors to release their energy and concentrate that energy at the same place at the same time. So that is interesting. I want to dig into that and know how you can possibly do that. What are the other things that make it a really great, shock generator as opposed to just something that, is a normal capacitor bank?
When you talk about, what made this technology possible today and how can we synchronize them? So just in Titan, on one ring, which is what we call stage, there's 17 bricks.
Mm-hmm.
So 17 bricks means 34 capacitor and 17 switches. And then we have 14 stages that actually stack those together. So that means that, you have 250 bricks eventually that you want to discharge within almost speed of light. And so how does that happen is essentially the engineering, the precision engineering that's required. So a main differentiator between an impedance match mark generator, which is what Titan is, and other type of pulse power systems like a linear transformer driver, also known as LTD or others, is so the impedance matching means that you can have the same load impedance as the driver impedance. And what that means is, if you can design your driver such that the resistance of the driver is the same as the resistance of the load, that means you can couple as much energy. But to go back to your question on timing,
because the other one, what's the name of the other kind? The
linear transformer drivers.
That guy. So those kinds, they are not impedance matched, which means that there's a difference in the resistance or whatever of the thing that you're trying to put all that electricity into and the capacitors themselves, right? Like that, the part that's shocking and the thing that's being shocked. Is that the case?
I mean, LTDs are close enough, so you can still do some impedance matching. But the problem with them is that you have to trigger every single switch individually. So you cannot actually, because there's a ferromagnetic core for insulation, so then there's a lot of problem on how do you get this much high voltage to go through a driver and couple to load. And so the main innovation in the IMG was just having to trigger the first three stages. So we only have to trigger 17 switches times 3, essentially. So 51 switches, 51 switches, essentially. And then have only those trigger within less than 2 nanosecond difference. And then all the other switches
goes through the rest of it.
Yeah, essentially. It's like a dominoes effect.
Okay,
and dominoes effect is moving almost at speed of light.
Yeah.
Because it's just the electrical discharge is trickling down. And so that allows it to be much more efficient and also simpler from like an engineering perspective. So just triggering one stage or 3 stages will help trigger eventually 10,000s of switches down the line, which make your engineering much simpler. Because now you have only, a few switches in a large scale machine that need to be triggered.
That makes sense, and that's an easier challenge because you only have to make sure that those three things are like very perfectly synced, as opposed to however many of them are in the total system.
Correct.
And then the other part of it that I think is interesting is like just to like take sort of a step back. Like the whole point of it is that there are these capacitors that are originally, and tell me if I'm wrong, I might be totally wrong about this, but there's capacitors that are originally in series, and then when they are triggered, basically the charge of the capacitor jumps a gap and turns the whole thing into a parallel thing. So all of those charges are now stacking up on top of each other, which is what you're saying. It's like we ignite a ring of these things. We do actually 3 of them, is what you said, and then that shock by itself is now enough to just bridge that gap without having to introduce another like external shock. Is that a fair way to say it?
Yeah, that's correct. I mean, we charge the capacitors in parallel, we discharge them in series, and eventually the self breakdown voltages mean there's enough voltage in the circuit that will self trigger the next one, and that creates the dominoes effect where all the voltage starts adding up. And then eventually you're way beyond the threshold of a switch that's breaking down. Like, what's the voltage that's required for a switch to break down?
Right.
And that makes it way more efficient and theoretically should go at the speed of light. And now we're pretty proud to be the first team that's experimentally demonstrated the engineering of the impedance match Mark generator at high energy and shown that we could couple around 85% of energy coupling efficiency with a matched load.
Does that mean that 85% of the total initial charge of the capacitors is all seen at the end? Is that what that 85% means?
Yes, essentially, like how much the energy stored in the capacitors, how much of that is coupled to your matched load.
Okay. Yeah, perfect. So how different are the 3 versus the rest of them? The 3 that are actually triggering. Are they all sort of like, they have the same oil thing that separates
They're
them?
Exactly the same. There's no
really?
difference at all. But you're just adding the voltage enough such that, by stage 3, I mean, also at stage 1, it could happen. At stage 1 or stage 3, you have enough voltage in the circuit that's self-breaking all the others.
Okay. Did I read correctly that those 3 though are externally ignited? Basically, like you have.
Yeah.
Did you call them BFMGs? Am I? Can I guess correctly what BFMG stands for?
Take a guess.
Big fucking Marx generator.
Yes, exactly.
Okay. Yeah. So you're triggering them with 3 BFMGs, and those are separate, like external to the big tank thing. Is that right? And then that's how you get. So it's like, it's kind of fun. It's cool. It's like it's nested pulsed power. It's like you're using the concept of Marx generation to trigger the first 3 stages of Marx generators, right?
Yeah, exactly. So one of the also critical engineering is how do you trigger such a system? Like, how do you get it all to start? And this is what we spent a lot of time building our own proprietary technology on building this triggering system that's less than 2 nanosecond jitter, which means there's less than 2 nanosecond difference with the pulse that's being sent to the stage. And now we were able to build a whole sequence of a triggering system, including the BFMG, but also includes a trigger generator, a pulse generator, and initially starting with a digital delay generator. And all of those essentially lead to a pulse that starts the voltage adding from the first 3 stages and then gets the voltage to a point where all the rest of the stages can be self-triggered.
Okay. Do you mind explaining what those 3, I think you named the 3 different parts of like that triggering system. Do you mind explaining like what each of them does basically?
Well, think about them as they're all Marx generators. It's just like a different way. Like, you want to get to the pulse energy and rise time and voltage that's required in a very fast amount of time. And we're just doing a technique that allows us to add up the energy, to increase the energy, the voltage, and the rise time to get to the pulse required to trigger the first stage and then second and third.
I mean, it literally sounds domino-ish, right? Like it literally, you knock over a little tiny one to begin, and you can be very, very precise when you do so. That ignites a little bit bigger thing, which ignites a little bit bigger thing, which eventually is like this massive system full of, a tank that's as big as, a water cooler outside your house or something.
Yeah, it's actually pretty big. It's really cool. I hope one day you get to see it, but it's pretty high and big, and it's nice. But at the same time, is a third of the size of how do you get the same amount of energy or power from existing systems that are used today. And to double down on your point, where essentially some people, professors in the field that are pretty well known, they say pulse power is black magic because essentially it's the same type of basic components. There's nothing too exotic, just capacitor switches, resistors, inductors. And with all of those, you're just playing with the numbers to get your pulse to head the right shape, the right rise time, the right voltage to get to trigger or start a process.
Yeah, it's not that crazy. Like I think that there are a bunch of YouTube channels actually where people have built them in their house and they have these
Yeah.
crazy like arcs that are coming off them and stuff. Like I'm sure you've seen those, but they're like the crazy like electro boom, or is that guy's name? I forget. But like there's a bunch of YouTubers that have like built them in their backyard. So it's not like exotic physics. It's not like, some far flung, which honestly is how most people think about fusion today. I think it's like, we know theoretically it's possible, but like when's it ever going to actually happen? I mean, your version of this is very practical in that people can build them in their backyard. It's just a matter of scaling it up and being big enough that it actually can generate some sort of useful effect.
Yes, you're absolutely right. I mean, the basics are really simple. So what we just needed to do is to show that this could happen at larger scale and also get to high energy, high power of a short amount of time, which means the technology, the baseline technology required, like the energy of a capacitor, the inductance of a capacitor, which means like the form factor needs to be small and like the amount of voltage you can charge them and how long do they last, right? So if you can get to this much capacitance and voltage out of a capacitor, how long will it last? What's its lifetime? So this is essentially building on technology like capacitors, switches, even laser triggering for precise timing that allows us to take this technology and use it for higher energy, higher power at the right rise time required for starting a fusion reaction.
Totally. I mean, the like how much of this? So there is a machine that is done, the Sandia Labs Z machine. Like this exists. There is one of these in the world. How different is your machine from the Z machine? And I mean this specifically from like, did you make any sort of different design choices? Like, okay, Z machine is more of like an academic thing. Like it doesn't really like ultimately need to generate be used as much, or maybe it doesn't need to last as long or something. Like, are there different sort of design choices that you made that led your machine to being very different from Z machine, or is it kind of the same, maybe bigger or smaller? Or I'm curious how they differ.
Yeah, absolutely. So the Z machine has been around since like 1990s and it was refurbished in 2007 as it exists today. And it's based on a traditional Marx generator that takes 6 stages to get to the pulse lengths or pulse widths required for fusion to happen. And throughout that process, you lose 50% of your energy stored. Right. And also the lifetime. So at the end of the 6 stages, you have one switch that has to withstand megavolt of voltage, which means this switch is going to need a lot of maintenance and won't last for many shots. So Z today is an incredible machine, is the world's largest source of X-ray, is an incredible device that's used practically for supporting the National Stockpile Stewardship Program. But when you think about what is required for a fusion pilot plant to generate power, you need a repetitive system that's more energy efficient. And so what our driver does is it replaces the essentially all the pulse forming line, the 6 stages of the Z machine, into a single stage, and that allows to double the energy efficiency while going a third of the size if you were to build the next Z machine was the same traditional Mark generators that they use today. And through that, the highest voltage that's seen on a switch in Titan is 200 kilovolt, versus on the Z machine, it will be like 6, 7, or even more. And so in that case, you're increasing the lifetime of all your components by over 1,000 times. So this increases the rate of how much can you fire the machine. With Titan, is 0.1 hertz is totally reasonable.
Every 10 seconds.
Yeah, every 10 seconds, you're able to increase the lifetime of your components by at least 1,000 times. You're doubling the energy efficiency, close to 90% of driver efficiency. You also are going for a third of the size. And so all of those, we believe, are really critical elements that were required to build the next generation of the Z machine and start working on the actual target design. And for the target design, so when Sandia started, I think they increased over 10 years or so oh yeah, over the past 10 years, they've increased their neutron yield output by a factor of like 10,000x.
Oh,
So
wow.
the same machine, same stored energy, can now generate 10,000 times more neutrons just because they've improved
Wow.
the target design. They've started doing some laser for preheating. They squashed some instability by premagnetization. So they reduced the MRT, which is called magnetorally Taylor instabilities, and others, just by creating these tests. And imagine if we had 10 years worth of Z machine experiments in 1 year. What's the rate of change? What's the
Totally.
rate of learning that we can go to iterate through designs and get to like a higher yield, which is like fusion yield design concept. And that's essentially what Titan will enable us to do, and what Fuse plans to use Titan for, is to create an intermediate facility that allows us to do 1,000 shots per year versus the 200 shots or so that Sandia does on the Z machine. And so that increases the rate of learning from a decade to a single year or month.
That's awesome. That's so cool. I mean, I think so when you set out to do this, when you set out to make this, how much of this was just like already in your head versus you had to go learn it by just building the thing and, doing some test shots and then tweaking and, doing that iterative approach that you just talked about?
Yeah, so we started out by actually working on still on pulse power technology, but on a slightly different path of Z-pinch. Still the same physics concept of like using, imploding gas, but now we have to implode a solid liner. But so when we started out, we learned a lot from Sandia, so we're pretty grateful for them for having published a lot of their science and put it in the open public, as well as other people in the community. But at the same time, there was no textbooks reference. There was no, like, this was never built. And so we had to learn and build an engineering roadmap. And, the team really, we start asking ourselves, what are the biggest risks in doing this project, and how do we retire them iteratively? So, for example, we started by just designing a brick.
Yeah.
And we designed 6 different bricks to get to the inductance required experimentally to verify, like, this can work. Can we hit the right sum we need? Then second, we started with just one stage and say, let's try to trigger it. And we iterated a couple of months to refine our triggering system to get to the requirements that we thought we need to match what was initially required. So we really had to build and learn a lot. I mean, we've done some mistakes, and the team has learned and solved them and built. Throughout the process, we built a lot of trade secrets and also proprietary technology that helped us eventually get to matching as close as 99% of simulated results that some experts in the field have predicted, and we were able to match them as almost 99%, which makes it sound almost not true, but it's now.
Yeah,
it's now.
that's awesome.
It's now done, and the results are all out.
We talked about some of the technical challenges, or really the engineering challenges of building this thing. We talked about how hard it is to synchronize and how hard it is to trigger and how you've sort of tackled those things. But there's much more. I mean, we're just barely hitting the surface of all the things that it takes to make one of these that actually works. One thing that I really wanted to, I think you, in your paper, you highlighted 3 different things. It was like synchronized triggering, pre-fire rate, like minimizing the pre-fire rate of the different switches, and then also pulse shaping. So let's talk about those latter 2. I mean, maybe just start with the second. Like, what does it mean, and how do you decrease that pre-fire rate?
Yeah, absolutely. So Titan is the first proof of the concept to show that this technology actually can work and is supposed to work as we thought it would, or some other people have invented it. But it's still, when you think about what it's required for, like, a production scale and using it reliably, we have to think of all the small engineering, well, not small, but all the engineering details that will allow us to use this as a primary driver for, like, any investment of multi-billion-dollar scale, which eventually the government may want to do, or others. And there's not much risk tolerance on those faults. So pre-fire rate is a switch may go off before you want it to do. So it's pre-fired on its own. Either it's seen a voltage spike, or there was EMI noise or anything in the system that caused it to pre-fire. And so when you're just using a voltage breakdown, then that may happen because the switches may pre-fire at like maybe 80% of their total self breakdown voltage. And so that's essentially what that means. And so now we're working in V2 and using a laser triggered gas switch, which would reduce the pre-fire rate or the self breakdown voltage of the switch at 60%, which would minimize significantly the pre-fire rate. And the reason why it matters, even if it's 1%, if you have 10,000 switches in your facility or 100,000 switches, means that at every shot, there's
Yeah.
going to be 100 or 1,000 of them that will be fired.
And are those just losses? Like, do you only lose those switches from the chain, or does it also impact, like, if one switch goes off, will it trigger the next one? Will it be enough to trigger the next one by, like, in the chain, or does it just lose its own voltage, basically?
It would, but you may lose some efficiency. You may lose some of the coupling, resistive coupling efficiency. So you may lose efficiency. You may also have it, go off before you intended to.
Yeah.
Right. So as your other system is working together, you may have a shot before you want it to happen. And so that means it's unoptimized, and we want to get it to be at a point where we know when we're firing, and we can actually reliably fire repetitively at 8,000 shots a day or something. That would be at the scale that's required for a fusion pilot plant.
Yeah, I mean, it seems like it's one of those challenges that's just like a straight up trade off. Like on the one side, it's like, okay, we could really isolate these switches from each other and make it so there's no pre-fires at all, but then that makes it hard for the actual shot to happen. But the alternative is that you make it too easy for those things to trigger, and then you have more pre-fires. And so, like, how did you strike that balance right? Like, was the oil decision like made as a result of trying to reduce pre-fires? Because the switches are like floating in oil or something, right?
Yeah. So the oil is just essentially like high dielectric content, which means that like it isolates the whole system electrically. So as you were talking about before, when you look at YouTube, there's like arcing.
Yeah.
So any mistake in our system will cause a massive arc, because you're dealing with very high voltages, and so we have to be really careful about isolating the system really well. But the fundamental pre-fire happens when if a switch is rated for 200 kilovolt and you're trying to get as high to its maximum voltage, that's when the pre-fire rate is happening the most. So if you can reduce the self breakdown voltage that's required from the top maximum of the switch, you may be able to significantly reduce its pre-fire rate.
What does that mean? So the self breakdown voltage means the amount of voltage that needs to be in there for it to close.
Essentially.
Okay, got it. So you want to be operating it further from its maximum. You want to have more tolerance basically for
Essentially, you just don't want to hit, like, if it's self breakdown voltage was 180, you want to try to not get to the limit or to the 80% of where that is.
Yeah.
The farther you are from the peak, essentially, the more you can control the pre-fire rate.
Makes sense. You're not operating at a full tilt. So you have enough margin in between.
Yeah, and we're building some new technology right now in the lab. We have a new setup, like a test bed, just for thinking about how do we reduce the pre-fire rate. And so we're very excited to continue working through those challenges and opportunities, essentially, to mature this technology further and further.
Cool. One of the coolest charts that I saw in the entire paper was the one about the pulse shaping and how this is so cool because it's an experimental result. It's not like the theory of hey, what'll work, but you tried this. You tried. I won't give it away. Tell us about how you did the pulse shaping and basically what it means for the performance of the system.
Stepping back a second on why pulse shaping matters. So this driver can be used for fusion load, can be used for X-ray, can be used for high energy lasers, could be used for a variety of different applications. And what that means is, all those applications will need a different pulse, whether it's 200 nanosecond, 100 nanosecond, 400, 1 microsecond, etc. So there's different pulse characteristics. And so what we wanted to demonstrate, and because this is usually built with a specific geometry that's optimized for one load, what we wanted to show is that this could be varied with no mechanical changes. And so we built our own, also proprietary air delivery system where we were able to control the pressure of every switch independently with just software. So you sit behind a computer and you can monitor and control every single switch pressure. And by varying the pressure, we were able to, vary the pulse widths. So you can say, I need 200, 300 nanosecond pulse. You don't even walk to the machine. You just change the pressure on the screen on your control interface, and then that allows you to do variable pulse shaping. And this is something we're really excited about. It's results that got us excited. And as we scale now to 14 stages by the end of the summer, we'll see that those pulse shaping experiment was 14 stages, which we expect to be significantly more. So, we're very excited to see that. And this also will mean that this driver could have a variety of applications without doing any mechanical changes.
Super cool. And is the reason for that basically that if you have higher pressure in the gas switch, that makes it more likely to set off or something? And so you're making it easier to set off, which means it sets off faster, which allows it to be like variably shaped. Is that the simple way to think about it?
Think again about how we talked about self fire. So when you have self breakdown voltage, it's also a function of pressure in a sense. So you can vary your self breakdown voltage with the pressure gradient. And there's other factors involved, but at a high level, if you vary the pressure, you can vary at what point is the switch essentially breaking down, and then in that way you can vary the pulse. You can get to vary the pulse widths.
That's awesome. So you're currently in the stage where you've built one of these. You've done a bunch of test fires, and I think did you actually just like tear it down so you can make a bunch of improvements and build up another better one? Is that
Yeah, we actually had to break it. We have to disassemble and reassemble it a couple of times. Fixing some engineering challenges, also improving it. Right, like now that we've have some experimental data, there were areas of improvement that we thought about to improve the operational efficiency and also the system overall. And so we've had to disassemble and assemble it a couple of times, and now we're in the process of building it for 14 stages, so more than double the power that we fired before. So, we're very excited about that.
So when you're designing the system like this, do you end up building a lot of this stuff in-house? Or like, I'm basically trying to figure out like where on the range of like fully outsourced, we're just getting all these components sent to us in like full assemblies versus you just build it all yourself. Like I'm sure you're not building your own switches, but it's like where in that range are you? And how do you think about, the risks that come with not building in-house versus the challenge of building things in-house?
Yeah, so we're over time continuing to build more and more in-house, and like relying on external supply chain is very difficult. Obviously, hard to meet timeline specifications. Yeah. When you're doing something at extremes, people will claim to have certain specifications, but they don't even have the facilities to test those components at the levels that you are running them. Right, so it's really, how can they spec it out? They don't have a facility to test a component at those voltage or current levels or energy levels. And so over time, we're continuing to vertically integrate more and more. And even today, Titan has 40,000 parts, and we've had to significantly, a third of our facility is probably manufacturing and electronic assembly and so on. Not probably, actually more. Maybe 2/3 of the facility is just for
getting parts in house, making sure that they actually work according to the spec,
or building in house. We have our own, machine shop. We have our own electronic assembly. All the control system circuits were built, assembled, soldered at the facility. So we really build most of the systems in house.
Crazy, yeah. I imagine that's a huge concern, or like not a concern, but it's a huge thing you have to think about when you're just going to try to build either one at full scale, which means stacking multiple of these Titans into one machine, which is crazy, or if you're just going to build a lot of them and deploy them for different reasons. Like I'm sure that's a huge thing that you have to think about and figure out as a company.
Yeah, so we're very focused on that. Other fusion companies are thinking more about, showing the science that it works, etc. We're not concerned about that. Sandia has done decades of work in other U.S. national labs, and we're pretty confident that we're going to get to the yield required. So what we're really laser focused on is how do we mature this driver technology and can manufacture it at scale. And so we start coining the term of we want to create a tera factory that can create 1 terawatt a week or eventually a day to build those drivers at scale.
Awesome. So that actually dovetails perfectly into talking about what are these things used for, because like, why would you need a bunch of them, or like, why would they be useful to people? I mean, and this, just to like be totally honest, is one of the big knocks on a lot of other fusion companies, which is they're trying to build fusion reactors, and that's it. And until they get there, however many years in the future that is, there isn't really much that you can do with these machines. They either are working or they're not. They're like, developing useful science and helping us figure out how to do this, but there's no actual commercial use for this stuff before it's actually made. That's different for you. And so I wondered if you want to just talk a little bit about super high level first, like what are the uses for this kind of thing and why can it be useful before it's actually generating power via fusion?
Yeah, absolutely. So when you think about the Z machine at Sandia or the National Ignition Facility at Livermore, that's all over the news for being the first facility that achieved, scientific fusion break even. Those facilities were not funded for energy, right? Those were facilities that were funded for national security to advance the stockpile stewardship mission. And so what that tells you is these machines are producing massive radiation that are critical for supporting, the national security agenda and mission. And when you think about Titan, it's a new driver that could be a source of radiation. It could power high energy lasers that are, we're seeing high energy lasers being more and more useful today and on the battlefield. And there's other applications for them. There's also radiation is used to produce for in medicine critically, right? Like there's critical medical isotopes that are generated through radiation. There's some critical therapies that are relying on radiation. So radiation is good. It's not just bad, which is what people associate usually with, 3 Mile Island or Chernobyl, etc. And so Titan is essentially a pulse power driver that, depending what you put as a load, you can use it for various radiation application. And so what we're excited about is to use this on an interim scale to use Titans to essentially create radiation effects and nuclear effects. So that means creating similar conditions to natural space radiation environments or, man-made or human-made, essentially, threats. So, and with the current geopolitical state, there's more and more, concerns about some foreign nations of using some strategic weapons that could create conditions that we want to be prepared for and to be ready to have our system be able to survive and respond effectively. And so that's why we're very excited to use those Titans for to power radiation effects facilities as well as power other generators and all the electromagnetic spectrum.
Totally. I mean, we care about that in space a lot, obviously. I mean, my company, Astronis, we build small satellites for the world beyond low Earth orbit. And so people don't know this. The world is engulfed in a huge radiation belt. There's actually, we're protected because there's this big cloud of radiation that's trapped by the magnetic fields of the Earth. And so we don't have the luxury of being within that out where we're building our satellites. So we're actually our huge buyers of radiation. Like one of the biggest things Astronis has done as a company is go to Texas A&M or these other places that actually have radiation sources and use them to test electronics and see what's going to live out there and what's going to not. So, I mean, I personally, like in my own work, know that this stuff is useful, but you're right. People do think that radiation is scary and bad and evil and whatever. It's just the thing that is bad after there's a nuclear meltdown or something. But there are uses for radiation. And so those are the kinds of things that you're going to be able to sell, services you're going to be able to sell to people that want it. With these reactors.
You're exactly right. And today, if you think about if you are as Astronis, I'm sure that you've had to face significant challenges and getting even time at TAMU, at the cyclotron at Texas A&M.
Yes.
So most of the facilities that operate or provide those radiation effects are in the government facilities or at some very select, universities that work very closely with the government. So it's a really difficult process to get time at those facilities. And if you're trying to qualify a system, you have to go take it to other third parties that will qualify it, other companies that will do the testing and experimentation. And so we're working to make this process much smoother. And with the rise of all the aerospace companies and just the industrialization of space, there's going to be significant more demand on radiation facilities, and Fuse wants to become the company or the place, the one-stop shop where people who are looking for radiation, so we can provide radiation as a service and cut down a lot of the inefficiencies of the system today as it exists.
Totally. And so why don't you talk just a little bit, taking a step back of like what's actually happening at the center of this thing. So we have the Titans that fire. What happens once all of that power is consolidated in a very small place at the exact right time? Like what is actually happening to produce neutrons or produce gamma rays or produce X-rays or whatever comes out of it?
Yeah, so you can put various loads. So for fusion, we put literally a solid liner. So you can think about it as a can of literally it's made of high Z material. So I think stainless steel, aluminum, etc., lithium, beryllium. Inside of it, you would put the fuel, so it would be deuterium, tritium in our case, which are two isotopes of hydrogen, essentially. and then the electromagnetic field that's generated by all the titans will implode that can, and that implosion will create the density temperature for the 100 nanosecond implosion time, roughly create those neutrons. Now, if you want to do X-rays, you can use other sources like wire array implosions. So instead of having a solid liner, you'll just put wires in an array, like in a cylindrical array, and could be, titanium, different type of high Z, again, material wire arrays that you'll just implode with an electromagnetic field, and these will produce very high energy X-rays. And so depending on what you're optimizing for, you can put a different target at the center of the machine.
But the electricity isn't literally flowing through the load, right? It's flowing through something around it, or beside it or something, and it's the magnetic field that's created by that is actually imploding the load. Is that true?
Correctly. So,
Okay.
so essentially, you have an so you have after the driver, you have something called a mitral, which is magnetically insulated transmission line. So think about it as a glorified cable, like
Yeah.
that you take out of a generator, and then you connect electrically with a cone a target. So it's electrically connected, and then J cross speed, still Lorentz force, basic thing.
Yeah.
Essentially, if you have a current, there's a magnetic field
That wraps around right hand. Yeah.
yeah, and then you have a force that's radially inward, and that force will crush essentially and cause the implosion, and that's essentially the process that's happening there.
Got it. Yeah, I saw a good visualization of this that maybe we can put up on the screen or something. It's like if you had a tube, like just a hollow tube that was struck by lightning. Like you have the electrical current that is passing down through it,
Yeah.
and then you have the radial. You're like right hand ruling or whatever. Like there's a spiraling magnetic field that goes and that pulls in. So it's literally just crunching in to create that crunch. But the amount of electricity you're delivering is so intense that crunch is enough to like literally implode the material. Like,
Yeah.
and I don't know, does implosion have like a specific technical meaning in this case, or does it mean just like crunching down really hard? Like, is there some criteria you have to meet for it to be true implosion, or is it just like the degree of implosion is so high that it creates fusion like conditions?
Well, the implosion is just an implosion. There's various specific technicalities, but what you're considering, what matters is the thermonuclear conditions. So, are you creating the conditions required for a thermonuclear reaction to happen? Which means there's beam target, there's beam fusion, and then there's thermonuclear fusion. And in those other cases, you're having particles that are hitting each other that are creating neutrons. In thermonuclear environment, you're able to break the electrostatic force because you have the thermonuclear conditions that allow for the atom to come together. And so when you have the thermonuclear reaction, you have predominantly monoenergetic neutrons. So you have all the reactions being in the same energy predominantly. And so that's really useful for fusion because that's scalable. Right. So
What does that mean? I don't know what that means. The monoelectric neutrons.
monoenergetic, so they all have the
Monoenergetic.
same energy essentially. Versus like if you have a beam target, like you may have neutrons from a varying spectrum of energy. And so, but that means also that you can get to burn and get the reaction self-sustaining itself. If you have enough of those particle fusing, like you may get a burn and this reaction self-sustaining itself to get to a proper ignition.
Got it.
Right, which is what all fusion people are like striving for at the end of the day. And these are the conditions that we will need to get much higher current to get there. Right now, based on the work mostly published by Sandia and Fuses published our own peer-reviewed paper, we're thinking that's somewhere on the 60 to 70 mega amp, somewhere between 50 and 70 mega amp scale to get to those conditions.
Got it. So for the initial Titans and like the initial product basically, which is whatever like gamma rays or neutrons or whatever, how do you kind of quantify the amount of neutrons or product that you're putting out? And have you done tests to see what those values would actually be?
Yeah. So Titan produces not as much neutrons because it's just one driver. You need many of them to produce significant.
Because it's like 0.6 mega amps.
Yeah, essentially. So you'd need to have like 15, 16 of them to get to the 10 to 12 mega amp range, which is what's necessary to start doing an implosion.
Got it.
But we have other neutron generating facilities in our facility, and we're right now licensed by the Canadian Nuclear Safety Commission in Canada for our neutron measurements, and we have a full radiation
That's such a cool
essentially.
license to have. Of all the like permits that you can have, the ability to produce neutrons is really freaking cool. And you
Yeah.
have it's like amount per year, right? It's like a number
Yes.
of neutrons. That's so cool.
Yeah, you have a certain threshold. So we're right now licensed for 10 to 13 neutron per year in Canada. So we're working on our licensing here. And that essentially, the way you do that is there's many different techniques. You can do like neutron time of flight measurement to get the energy of the neutrons. There's also different, you can do silver or, foil activation counting. So you can have different foils of material like silver or indium or other material that you would activate and see what's the energy of the activation, what's the percentage, etc. And you can have photomultipliers tubes, and different type of neutron diagnostics essentially that have been done for many years and very well understood, and we're just using some of those diagnostics techniques to be able to measure both the amount of neutrons, the fluence, so how many neutrons per area you can get, the flux, which means neutron per area per time, as well as the energy of the neutrons. So what's the like spectrum of neutron energy that you can get spatially and temporally?
Cool. So the neutrons is one product. What are the other things that a Titan by itself would be able to do?
X-rays, so flash X-rays, so producing high energy X-ray in a very short amount of time. And think about when you're passing, TSA security, right?
Yeah.
You're putting your baggage through X-ray. Now, if there's something more sensitive that you want to photograph, right? Like think of things moving really fast.
Sure.
And obviously, it's mostly in the defense side. But if you want to get a flash X-ray of high energy, then that will be really useful. And depending on the load, maybe even producing short pulse gamma.
So these are what we've been talking about are the things that you can produce now with kind of the current product. But you have ambitions to keep stacking these things and keep stacking these things and keep stacking them until there are these massive systems that can produce ultimately fusion.
Yes.
But do you mind just walking us through like kind of what is that step up in size for the different types and then what they can unlock?
Absolutely. So before specifically talking about our roadmap, I'll also just say about how we've thought about designing and why we've made certain choices. So from my perspective, standing today, and I'll preface this by saying, I have no PhD that married me to one technology aspect, but essentially just thinking about what are the biggest risks that are standing in the way of fusion today, and what's the path that's getting us there the fastest. So I don't care about what approach works. Like we just care about what works and how do we make it happen fast and as cost effectively as possible. And then throughout that path, we first looked at the results from the Z machine, and it's 10 times cheaper and also 10 times more efficient than a laser, and it's 10% of the size and costs essentially. And the first risk was, can we have a driver technology that's repetitive, that's scalable, etc.? And that's we built Titan. Now, the second risk is how can we couple those Titans and work on the target design so we can do repetitive? Because every time you fire the Z machine, there's significant damage to the chamber. So that chamber...
I saw that video. The videos are crazy. It's like deposited with like this soot stuff or whatever after every time it fires. It's crazy.
Yeah, so...
And it's those switches. You were talking about those switches that just get like fried at the end of it, right?
The switches get fried, but I'm talking about like where the target goes, like the chamber that's holding it.
Yeah.
The targets are mostly from the electrical current, but like the chamber itself has significant damage. And so how do you replace that chamber fast enough? For fusion, you would need to do that every 10 seconds or every 100 seconds or every second, depending on, your scheme and your yield, etc. So how does that happen? That's a pretty big challenge today. And so in our roadmap, we thought, great, we proved the driver. What's the next second best thing to de-risk? And it's repetitive operation. Doing this repetitively and also having a platform to scale the physics, to understand, what's the targets, how do these targets scale to like what's the right amount of machine to build to actually get the conditions for fusion. And so that led us to Z-Star, which is, a 10 to 12 mega amp facility, 15 terawatt. And that will enable us to do liner implosions. So that's enough going to do liner implosions. And our target is to fire that, 4 times a day or 1,000 shots a year. And so that enables us to learn about operationally how to operate this machine in a repetitive automated mode. And then from there on, scale to a full scale fusion pilot plant, which would be a 50, 60 mega amp machine at the conditions required for fusion to occur.
Cool.
And so when you think about, again, what is this used for? We talked about radiation, right? Well, fusion is creating enough radiation, but at a frequency like 8,000 shots a day, or depending on your neutron yield, think of 1,000 times a day at a unit economic cost that's reasonable for it to be commercially viable. So it's exactly the same process that these machines will do that the fusion technology needs is just radiation that's high enough for it to make sense from like an engineering and even wall plug efficiency perspective, repetitive, so we can do it from a 99% upkeep perspective as a baseload power source. And then third, cost effectively, can we sell this for an economically reasonable price for customers to want to buy it? And so right now we're working on all these three parameters through building these growing machines. And there's definitely customers who you give them just one shot a day, and that's more than what they're looking for in a sense from those large scale machines. So, we're just using this technology roadmap path as a way to fund our progress and also de-risk and mature the technology for fusion power.
Totally. I think that's the most confusing thing to me, just in terms of like this design for continuous energy. You mentioned the difficulty. It's like, how do you're imploding super violently this like piece of fuel at the middle, and you have to just plop in another one every 10 seconds or something. And let's say that happens. Let's say that works, and you figure out the like whatever 0.1 hertz version of this, where you're replacing fuel every 10 seconds and firing it every 10 seconds. What does that look like in terms of power output and like a connection to a grid or whatever? Is it like crazy spiky where you're having these like super big pulses and then there's nothing, or is it continuously generating power somehow? Like how does it turn continuous?
Yeah. So the way you would produce power from this scheme is like you take the neutrons and then you would have like a liquid blanket or some sort of liquid metal that will transport the heat out, and have like a steam turbine that's taking the heat and turning it into electricity.
Got it.
Right? So there's no direct interaction. So as long as you can fire at a rate
that keeps it hot enough and the steam going, and okay.
Exactly. So I think fusion will be relevant only if it can be a baseload power source that's producing continuous power, not intermittent. And so that will be a critical requirement to get to actually using it as an electricity source. In terms of, how do we get to high shot rate? There's many things. So think about the Z machine. Less than 5% of their shots are for energy purposes. So the amount of learning that was done on this is really minimal with very constrained resources. So I think the opportunity here is massive by having, a platform like Z-Star that can fire 1,000 shots per year that are focused, primarily, obviously will serve different customers, but primarily focus on the energy mission. And, the targets could be simplified. The mitral, there's now path for just from a material maturation perspective and riding on all the technology waves that have happened to actually get those the technology simpler and at a rate where you can replace it quickly. And if you think we print a Ford F-150 door, every second or so now. So every few seconds there's a door that comes out. So, and the target is way simpler than that.
Yeah.
So why can we not do it? And there's stamping technology. There's just robots today that are way more efficient that didn't exist in the 1990s when these machines were built. So I think there's just a lot of technology maturation wave and like advanced robotics and manufacturing that we'll leverage and will make this much simpler and efficient to build.
That's cool. I think another piece of the puzzle, which we really haven't talked about at all, is like the fact that you will be an enabler for other kinds of fusion as well. So can you just talk about like what parts of the system are actually helpful to other types of folks that are trying to figure this stuff out, and what you've decided to use or what you've enabled others to like use from your own learnings and all this stuff that you found from operating these machines?
Yeah, so Titan will be useful, as we mentioned before. So if you're trying to build a high energy laser, or if you're a laser company, if you think about the National Ignition Facility at Livermore, there's 400 megajoule capacitor bank, literally.
Yeah.
And so high energy lasers need pulse power driver. If you're pursuing any type of pulse power approach, there's various companies using that. They will need this type of technology. We're obviously geared more towards the high energy density side. So there's low energy density pulse power companies, it's not really probably as relevant. But anyone in the high energy density pulse mode will benefit from the Titan technology advancements, whether they use ours or just take advantage of the technology leap that we've done. I think that's going to be critical for all the industry.
So the mention of Lawrence Livermore is actually really interesting because they were the first to announce a Q scientific over 1, which is a ratio that most people probably have no idea what it even means. And I actually used to think there was just 1 Q. So I was like, holy shit, we did it. We made fusion. But there are lots of definitions of this thing. Would you mind telling us what Q is and then sort of how you're using a Q less than 1 machine to get to Q greater than 1?
Yes. So when you think about Q as a ratio, essentially energy out versus energy in. So what Q scientific means is just looking at the energy deposited on the target. So, for example, NIF has 400 megajoule capacitor bank. So they ignore that for the Q scientific because that's not relevant. What's relevant is how much that capacitor bank deposited on the target after the laser, etc., and how much energy came out. And from that perspective, they achieved, scientific break even from depositing a certain amount of energy on a target and getting more energy out. And that's huge. I mean, that's a major accomplishment for humanity and for the fusion field. So we should all be really grateful for what NIF has done. Now, the second step is from an engineering Q, which means from the wall plug efficiency. So how much power do you take to charge your 400 megajoule cap bank to how much energy you're able to extract out of the neutrons and actually use. And so that's what engineering is. And that's what Fuse is focused on at this phase. And then eventually there's Q commercial, which are you able to sell this electricity at higher cost than at a higher price than what it costs you to build it. Mm-hmm. That's what ultimately will make sure that fusion is commercializable. But for now, at this moment, Fuse is focused on Q engineering greater than 1. And then on the path to getting there, NIF has received billions of dollars and is critical for the nation's stockpile stewardship. And for the first time right now in history, the whole nuclear triad is being rebuilt in the United States, which has never happened since we've built it. And that's a $2 trillion investment over the next 30 years. So I think this is a critical technology that's required to continue powering the system. And Fuse is focused on on serving radiation as a service and selling radiation for Q less than 1 until we get to Q greater than 1 in a way that we can sell fusion power. And we believe that there's a path to create a multi-billion-dollar company outside of just pure fusion power. But this technology is directly aligned, as we mentioned before, just an amount of radiation at the frequency and at the cost that makes sense. And so we're maturing on those 3 parameters as we continue to grow.
Yeah, I think that the most interesting difference between, or like maybe this is wrong, you tell me, but like it sounds like the major difference between Q scientific and Q engineering is like the efficiency of the power that's being thrown into the system. I mean, the reason why the Q science could be above 1, but the Q engineering would be below 1 for the National Ignition Facility is because the laser is just really inefficient.
Correct.
So if we had a really efficient way that we could build deposit power onto something, that is what gets us from Q engineering over 1 to Q scientific, or Q scientific over 1 to Q engineering over 1.
Yeah, that's correct. There's 2 parameters. So one is the energy driver efficiency. And then second is, even if you think about NIF, they've increased their yield from their very first shots at the National Ignition Facility by not changing the capacitor bank. They increased the yield and the gain by factor of 100,000 or something like that over the past 10 years. So if they were able to do that, with the same laser energy, to get to much higher yield by improving the target design, the target material, etc. That's really promising because now there's 2 functions. You can increase the driver efficiency, but you can also increase the target efficiency. And then both of those will eventually drive, the Q engineering and eventually getting to Q commercial, where in an ideal world, I don't know if that's going to be 20, 50, or 100 years, where energy will be literally almost free, right? Because your cost is so cheap, your target efficiency is so high. And we're just producing a lot more energy than what it costs us to build it.
That's awesome. I love that. So that is the most grand vision. It's like the idea of energy too cheap to meter is it's been always the dream. But I think the single thing that I like the most about Fuse is that you have a very discrete path to get there. It's not that it's this future maybe in 100 years we'll get there. It's like, okay, we know the things we have to do. We're going to make these drivers really efficient. Now we're going to have this machine that can shoot really often so that we can iterate and we can get better at the target design. Like it's clear to me how you actually get from zero to or q minus one or q less than one to q greater than one. And that's the coolest thing I think about Fuse.
Yeah, thank you. I appreciate it. And we're also monetizing the whole path because radiation is really valuable. Good radiation is really valuable. And we want to continue to make that as available and use radiation as a service on the way to eventually radiation as electricity.
Hell yeah, that's awesome. So any place you would want to send people? Any like are you hiring? Are you looking for investors? Like what would you want from the audience?
Yes, so we're actually building out a new facility in San Leandro, California right now. So anyone who wants to contribute in any way or shape, I think, operations or even engineering, I think there's a big opportunity here to help be part of building out our new facility and contributing. And we're also, in the process of, fusion will require significant amount of resources and efforts. I think if you look back at humanity, there's no problem we haven't been able to solve. It just takes enough people with the resources and the sense of urgency required to make it happen. So, the sense of urgency is there from, from a climate perspective, but also from a geopolitical perspective. And so now it's just about the people and the resources. And so we welcome both of those.
Awesome. This was awesome. Thank you so much for doing this. This is fun.
No, thank you. This was great.